Well, welcome back, you little set of masochists. This is going to be the final installment in the essay portion of the free response for thermodynamics, and this is going to be my favorite set, and you've got to decide right now if this is worth your time, because again, I say we have a set pacing guide that we give teachers in our program to use, and we do things a little differently. So we put all of Thermo together, which means that there's going to be a dab of electrochem in here. So if you've done electrochem prior to Thermo, you won't struggle with that at all. There's also a dab of equilibrium in here, and if you've done electrochem prior to Thermo, you've also had a dab of equilibrium back when you did the Thermo, or a dab of equilibrium in the Thermo. So hopefully that won't throw you off. And then there's a little bit about drawing some Lewis structures, which you should have had in your first year course. So these three problems that we're about to do, or essays, free response questions, no calculator we're about to do, are actually very representative of what the test is like now. So that's why they're my favorites, because I think these prepare you better when you're getting ready to study for the exam in the spring. So even if you aren't ready to listen to this now, you should at least file away that this is a good one for you to listen to in the spring. So we are now off to the races. This particular essay had an 8-point total, and the mean was a lousy 2.99. Part of that's because it was number 8. There's a lesson to be learned here. You need to focus on the AP exam. You need to practice this skill in all of your exams. You need to start in the free response that looks the most appealing to you. This is the one I'm going to go with first because I'm going to make the most points on this one. The more points I start putting into my pile, the more relaxed I get, the better test taker I am. If you're good with Thermo and you saw that this was question 8, that's where kids should have started, because this actually was not a difficult question whatsoever. So the mean is not indicative of the difficulty necessarily. Sometimes there's a bigger picture going on about where it was placed on the exam. So most kids were probably running out of time by the time they got here and may have never even finished the question. All right, the dissolving of silver nitrate solid in pure water is represented by the equation above. All nitrates are soluble, so we know this is a spontaneous process. Is the delta G for the dissolving of this solid positive, negative, or 0? Justify your answer. Well, it's negative, because your solubility rules indicate that we know that this is a soluble compound, so at room temperature. So negative delta G, since silver nitrate is very soluble. Therefore, the reaction must be spontaneous. One point for that, with that explanation. Just doing a coin toss of going, well, I have a 50-50 chance, negative, positive, that's never going to get you any points. You must explain your answer, or prediction in this case. Is the delta S for the dissolving positive, negative, or 0? Well, duh. We have a solid, very ordered system going into these two sets of free-floating ions, so that's a big old giant increase in disorder. So positive delta S, since the very ordered crystalline solid, I know it's an ionic crystal, so I'm going to throw that crystalline word in there, is dissolving to form two mobile ions. That's why it's an electrolyte. That's why it will conduct an electric current. Charged and mobile is what you need for an electric current. So when you take the solid, they've got charged particles, not mobile, locked into a crystal lattice structure. When you throw it into water, then it dissolves, and now the silver ions are separated from the nitrate ions, free to move about, and can carry electrons, thus an electric current. Not that it asked that, but, I just got this, I'm just compelled to teach at all times. All right, so the solubility of silver nitrate solid increases with increasing temperature. So what would that mean? That means that it's going to take heat in to drive the reaction to the product side, so therefore it's a positive delta H. It's endothermic. So what is the sign for delta H for the dissolving process? Justify your answer. It's a positive delta H, like we just said, since adding heat energy drives the reaction forward. Or you could say that it shifts the solubility equilibrium to the right where products are favored. There's lots of different ways to say the right thing, but you've got to get an explanation down that makes sense. So when you add heat energy, you're driving that reaction forward to make it dissolve more and create more of your ionic products. Is the answer that you gave in part A consistent with your answers to part B and C little I? And the answer to this is yes. Let's think about this. And this is one of those moments where you may have to think first, so you may want to leave yourself a space to come back and write your yes or no. But what do we know? We know that we have an endothermic process. We already figured that out. Let the problem lead you. We know that delta H minus T delta S and we know that delta S is positive. So now let's think about this. We also were told that as heat was added, that drove the process forward. So what do we have? We have a spontaneous process, so we know that that's a negative delta G. How does this happen? I've got a positive term minus another positive term. So when this term becomes large enough in magnitude to override the enthalpy term, then I get a negative delta G. So now I'm going to try to put that into a little bit more eloquent an answer. So the answer is yes, it is consistent. A negative delta G naught spontaneous reaction is consistent with the qualitative, is that how you spell qualitative? Qualitative, I think so. Calculation, qualitative. Thank God spelling doesn't count. Shown below. As temperature increases, the positive T delta S term increases and is subtracted from the positive delta H term. Therefore, a negative delta G term is obtained. Again, many different ways to say that. Okay, so that was fairly straightforward. Thermo got a point back on part A with an explanation, got a point on part B with an explanation, and a point on part C with an explanation, which could explain the mean of almost 3 on this question. Kids may have known thermo, and then get to the second half where it's electrochem, and it's traditionally like chapter 21 in the book, 17, 21, somewhere way late in the book. And they may have never ever done electrochem. A lot of kids, unfortunately, walk into the exam without doing that, when it's tragic, because I think it's actually the easiest unit in the entire course. So now what do we want to know? Well, now they're switching gears on us to electrochem. How do I know that? See these E naughts? There they are. So we're in the land of electrochem. You got to expect easy electrochem here, because they coupled it with thermo. So if it was just pure thermo or pure electrochem, you'd have to expect a more difficult problem. That's why I kind of like this, putting two different ideas together. I think it actually makes the questions easier for you. All right, so the compound NaI dissolves in pure water according to that equation. Some of the information in the table of standard reduction potentials given below may be useful in answering questions that follow. An electric current is applied. Ooh, that means we're into electrolytic, not galvanic. And see that 1A metal right there? It's not going to be oxidized or reduced. Water takes its place. If you didn't know that, you should go back and review the electrochem notes on electrolysis, because neither polyatomic ions nor 1A metals ever participate in electrolytic processes. Water takes their place. The question is, would it be an oxidation or a reduction? So I know that's not going to be used at all. So I've got an electrolytic process and I form iodine. Alright, so the first thing they want me to do is write the balanced oxidation half reaction for the reaction that takes place. So my oxidation half is going to be 2I minus forming I2 plus 2 electrons. Get a point for that. Next, they want, guess what? They want me to write the balanced reduction half reaction. Most kids tried to reduce that sodium, but ain't going to happen because alkali metals don't do that. The fact they're called alkali metals is kind of a hint, too, because you should pick the one that's going to make the hydroxide ion. That's where they get their name, alkali metals, because in water, that's what happens, is it splits water into hydrogen gas. That's the kaboom factor. And then also releases hydroxide. So we want a reduction half, which means we want the one that's got water, plus 2 electrons, because reduction is gain, making hydrogen gas. I'm going to put an up arrow for gas, but you don't have to. 2 OH. You do have to put that minus sign, though. All right, you get a point for that. So which reaction takes place at the anode, the oxidation or the reduction? Well, that's like what I said earlier. I think electrochem is one of the easiest units because we have all those goofy little mnemonic devices to remember things, and anox, and red cat help us out with this question. What do you want to know? Which reaction takes place at the anode? That's my an for anox, so the answer is oxidation. Oxidation always, whether it's electrolytic or galvanic, always takes place. I don't get to say always very much. So can I do it one more time? Always takes place at the anode. All electrolysis reactions have the same sign for delta G. Well, yeah, because you're having to apply the energy in the form of an electric current. So you're having to add energy into the system. So they're all positive delta G naught. Is the sign positive or negative? Justify your answer. Sometimes the easiest question on the entire problem comes at the very end. Positive delta G, non-spontaneous. This is charging your cell phone, not using your cell phone. Since electrical energy or work, if you prefer, must be applied to the system, added to the system, that's hence the positive sign. The signs make sense if you will let them, for the reaction to occur. Okay, pretty straightforward. We are heading into our final essay. I'm as happy about it as you are. All right, so I'm going to copy that and paste it so I don't goof up my one clean copy, and make it big for you. And, ooh, table of values. Crap, I don't have a calculator in my hand. Those question marks? Yeah, I'm pretty sure I'm going to have to answer those question marks. This little copy here is not very good, is it? I don't know what went wrong with this. Also don't know why it's on a 112%. Is it any better? Ooh, it's worse. That's a little better. Smaller, but clearer. All right. Just for fun, just so you know, the mean on this question was equal to 2.09 of 8 points. The mode on this question, meaning the most often earned, was 0. Wow. That's just awful. So it was probably, again, the last question on the exam because you don't have a calculator in your hand. So pacing is everything, and don't let question 4, the first one you face without a calculator, take up any more than 15 minutes of your time that remains. So you can split your time across 2 other events. If you're hearing my phone ring in the background, I'm so sorry. I can't really get to it at the moment. You're more important in my life right now. So I'll try to ignore it. You do the same. Answer the following questions using the information related to reactions X, Y, and Z in the table above. And for reaction X, write the expression for the equilibrium constant. So kids probably got all freaked out when they saw the table and didn't realize that, some of these parts don't have anything to do with that table just yet. So you want reaction X. We're going to write the expression Kp for that, which means don't use square brackets. If you use square brackets, you've got no credit because this is a Kp, and those square brackets are for Kcs because those are concentrations in molarity. So Kp equals the pressure of CO, products over reactants, times the pressure of H2 over, don't put that solid in there, the pressure of H2O. Now, that's one way to write it. You could have also written it as parentheses CO, parentheses H2, parentheses H2O, but you could not write square brackets with all that. You don't have to put the parentheses even around the top part. So yet another way it could look and be proper. All of those are equivalent ways of expressing the KP properly. But again, the brackets were off limits. If you did brackets, dang it, lesson learned, you lost that point. For reaction X, will the equilibrium constant Kp increase, decrease, or remain the same if the temperature rises above 298? And justify your answer. All right, so what we have going on is that we've got, look at delta H, a positive delta H value, which means heat comes in on this side of the equation. That's the best way to think about this through Le Chatelier. So what's going to happen to the K? That's why they had you write the K, so you can now think about this in terms of K. So if I increase the heat, I'm going to drive the reaction forward, which means my terms in the numerator get larger, which makes an overall larger number, so Kp will increase. That was me thinking loudly. Here comes the writing. Since delta H naught for the reaction is positive, increasing the temperature results in shifting the equilibrium toward, to or toward, your choice of preposition, the products increasing the value of Kp. Okay, and there's many, many ways to say that and get that correct, but that's just my way. The other way you could answer that, aside from this way, is to tie delta S, delta H, or delta G in. So you could very easily have gone solely thermo on this if you wanted to. Delta G equals minus RT ln Kp. So you could go minus Ratlink. And it also equals delta H minus T delta S. So then you would have the ln of Kp, solve for that, would be either delta H naught divided by RT plus delta S naught divided by R. An increase in T then for that positive delta, for a positive delta H results in an increase in the natural log of Kp, therefore Kp increases. So you could have done math. I think that's the harder way to do it because it's harder to explain. But it's your call. Your brain works the way your brain works. There's no one better way than the other. For reaction Y, did I pay attention? Did I realize I'm switching to reaction Y, which I probably should go look at again, which is now CO2 gas plus H2 gas yields CO gas plus H2O gas. 2 moles of gas on the left, 2 moles of gas on the right. That means Kp equals Kc if they ask me that. It also means that I had a little bit of a positive change in delta S because I formed a compound from an element, if they ask me that. It's a non-spontaneous process. I see that positive delta G staring at me. All right, so let's see what they really want to know. For reaction Y, is the value of Kp greater than 1, less than 1, or equal to 1, and justify your answer. Kp is less than 1. How come? A positive delta G naught value for reaction, that's not very pretty, for reaction Y indicates the reaction is non-spontaneous. Therefore, reactants are favored in the idea that K is generally proportional to products over reactants. You can never forget what K really is. Okay, that's just a generalization. We put lots of extra details to it when we need to, but that's the big idea. Don't lose sight of the big idea. So reactants are favored. Therefore, Kp is less than 1. Because on that generalization, my reactant term is greater than my product term, which makes a number that is a true fraction that is less than 1. Again, there's another way to go at this. You could have said Kp is less than 1 because delta G is equal to the number, and delta G is equal to a positive 29 kilojoules per mole, and it's also equal to minus Ratlink. So for delta G to be positive, the natural log of Kp must be negative to get rid of that negative sign, because R is positive and T is positive, always, always, always. So the only way for this to be a positive value is for the ln of Kp must be negative, and the only way that happens in the mathematical universe is if Kp is less than 1. So you got math options, you got word options. You got to decide what you're the best at. It's time to decide what you're the best at, hopefully before you take the thermo test. All right, and then part D. For the reaction Y, still with Y, which is larger, the total bond energy of the reactants or the total bond energy of the products? Well, that's tied to enthalpy, so let's go take a peek again. For reaction Y, the enthalpy is positive. That means you didn't get a payoff. So what does that mean? That means the total bond energy of the reactants is larger, since the reaction is endothermic. Or you could have said positive delta H, same thing. Therefore, total energy required to break the reactant bonds, that's ugly, is greater than the total energy released when bonds are formed in the products. That doesn't really look like an M. All right, so I think of this as cost and payoff. Anytime that you have a positive delta H, you didn't get much of a paycheck. You put way more effort into the system breaking bonds than you got back out of it when the product bonds are formed. So they have got to constantly get some form of energy driven into the system if you want to make those products, if that's going to be your goal, is to make those products. All right, little e. Is the following statement true or false? Justify your answer. On the basis of the data in the table, it can be predicted that reaction Y will occur more rapidly than reaction X. All I see in this table are delta, S's, G's, and H's, which don't connect for squat to the rate of the reaction. So this is a big old giant false with an exclamation point. Thermodynamic data cannot be used to determine the rate of a chemical reaction. And as an aside, only kinetic data from actual experiments can do that. That's for you. You don't need to have that sentence. I'm just trying to make you understand why. All right, consider reaction Z. I gotta go back and look at Z. Consider reaction Z. All right, two COs. H2s are canceling. H2Os are canceling. You know what? If you look at Z, it should have dawned on you that what you got is one. No, maybe not. Let's see what they want to know. Oh, easy enough for the first part. Is the delta S for the reaction positive, negative, or 0, and justify your answer? Well, you've got 2 moles of gas that's converted to 1 mole of solid, so that's a big giant negative delta S. Negative delta S, since 2 moles of gas with high entropy are converted to 1 mole of solid with low entropy and 1 mole of gas, for a net loss of 1 mole of gas, thus a net loss of entropy. And there's at least 7 or 8 other equivalent ways you could have stated that. All right, determine the value of delta H for the reaction. Okay, we have to reverse both reactions and add them together to get what we want. So let's look at this again. I'm going to clean this up a little bit. You want me to determine the delta H value, so I got to work off of these 2 values. So I've got to be on the lookout for a Hess's law moment, where I need to get CO2 as a product, so I need to reverse this one. So I'm going to rewrite it. CO plus H2O yields CO2 plus H2. Okay, I need H2 to drop out, so I'm going to now be forced to flip this around too. I'm going to write CO plus H2. CO plus H2, and then C plus H2O. Okay, so what is that going to do for me? Water cancels, H2 cancels, 2 COs, check. That's all that's left on the left. Carbon solid, check. CO2, check. Got it. Okay, so I reverse both of these. So this becomes negative and this becomes negative, and I simply add them together. So I get negative 271 kilojoules per mole. If you want me to do that for the rest of them, I could do the same thing. That's going to change sign, that's going to change sign, that's going to change sign, that's going to change sign. I can play this game. I get lots of points out of this game. So reverse both reactions, whether you did it the way I did it and draw an arrow back up there, or whether you rewrite it from scratch, which I do not recommend because you have precious little time to waste on this exam. And this was for Z. It's equal to a minus 131 plus a minus 41 kilojoules per mole, which equals a minus 172 kilojoules per mole. And you can do kilojoules mole to minus 1. It makes no difference. Okay, so finally, a sealed glass reaction vessel contains only CO and a small amount of carbon solid. If a reaction occurs and the temperature is held constant to 98, will the pressure in the reaction vessel increase, decrease, remain the same over time? And explain. So we're saying we've got this reaction, 2CO gas in equilibrium with carbon solid and CO gas. So the pressure is going to decrease. How do I know? Well, it's stated that the reaction is going to proceed. So I'm not having to worry about that. Therefore, 2 moles of gas will go to 1 mole of gas. And pressure is all about gas molecules banging into the side of the container. So therefore, fewer gas molecules collide with the walls of the container. Therefore, the pressure drops. And there you have it. We are now heading into the 2009 B essay. So you're wondering, what the heck is that? If you haven't seen that on the worksheets before. B just means back, I don't remember exactly what year, maybe 2002? Maybe it's 2003, I don't remember. But the AP program got so large, and cell phones and internet and cheating got, global, shall we say. So they decided to make a different test because of the international date line. So anyone who lives across the international date line from the U.S. takes this form of the test. Don't worry, it's not easier. Lots of statisticians, an army of statisticians work for ETS, the Educational Testing System Corporation that makes the AP exams and the SAT exams. They know what they're doing. All right, in the boxes below, draw complete Lewis structure dot diagrams for N2 and NH3. These are two worthy of memorization, but if you need to work it out from scratch, then you've got 10 total electrons, because nitrogen's sitting in the 5A column of the periodic table. So I have 10 total electrons to put between two nitrogens. I put on one, and if I did ... I run out, so I have to make another bond and another bond. Nitrogen is the only diatomic element that is triply bound. And then your good buddy ammonia looks like this. There will be a Lewis dot structure diagram video in the future. I don't have it at this very moment that I'm recording this one, but you've done Lewis structures before. I don't think that's a big deal. Those are supposed to be easy points. And you would have gotten 2 for being able to do that, a point apiece. So then they want us to calculate the standard free energy change, delta G, that occurs when 12 grams of H2 reacts with the excess N2 at 298 according to the reaction represented below. 1 mole, 3 moles, 2 moles. Just pulling down the coefficients. I know that H2 is got a formula mass of 2 grams, 2.02 if you want to be exact, but I don't have a calculator in my hand, so I'm going to round that to 2. So if you give me, the way this is written with this delta G value, 3 moles of H2 are reacting with plenty of nitrogen to get to the 2 moles of ammonia. So if you give me 12 grams divided by 2 grams per mole, isn't that 6 moles? So that's twice as much hydrogen reacting, so won't you get twice as much G? So therefore the reaction is doubled. Reaction amounts would be a better way to say that. R requires a different verb, R doubled. Therefore, delta G naught at 298 Kelvin doubles to negative 68. I can do that without a calculator. Kilojoules per mole. I can even get the units right because I can copy them. Given that delta H 298 for the reaction is negative 92.2 kilojoules per mole, XO, which is larger, the total bond dissociation, are you tired of this question yet? We're going to ask it over and over and over again until kids can get it right. So if it's XO, energy exited the system when the bonds of the products were made, that means that the bonds of the products are stronger. So the bond energy of the products are stronger, since delta H is negative. Therefore, more energy exits or is released as product molecules form than absorbed when reactant molecules, let's say bonds, reactant bonds were broken. To say a molecule's broken is not really very accurate, is it? Better choice of words. Okay, a point for that. So let me recap the points so far. You got 2 points if you could draw the Lewis structure. You got a point for realizing that the reaction doubled here, and a point for actually doing the math right and getting the negative sign and getting the 68 and getting the units of the kilojoules per mole. It's a package deal. Then on part C, that was worth 1 point. 1 point with an explanation. If you actually did the math, you do a Hess's law thing on the math, that's fine too. All right, I just did it in words, but there's a way to do it mathematically as well, and that's quite all right. And then, where am I? Part D, that's also worth, well, Part C was a point. I already talked about that. Part D is also worth a point. So what are they asking me here? The value of the standard entropy change, delta S for the reaction, is negative 199 kilojoules. Explain why the value is negative. Well, that's easy enough, because what did you do? Let's look back at that reaction. You went from 4 moles of gas to 2 moles of gas. That's a drop in disorder. So the delta S is negative, since a more condensed, therefore more ordered, you could do either one, state is formed. As evidenced by, that's one of my favorite phrases. Have you figured that out? The conversion of 4 moles of gas to 2 moles of gas. So you need to write real sentences here, folks. You don't need to just go, it's positive because 4 moles of gas went to 2 moles of gas. That doesn't really explain that you understand what entropy is, and you are not likely to get your points for that. Assume that delta H and delta S for the reaction are independent of temperature. Explain why there is a temperature above 298 Kelvin at which the algebraic sign of the value of delta G changes. Well, go to Granddaddy. Delta G equals delta H minus T delta S. Gibbs free energy equation. That's what big people call it. I call it Granddaddy. Since delta S is negative, and what else do we know? What did we know about delta H? Wasn't delta H negative as well? Yes, a negative. I have to think this through. Yeah, because I'm subtracting a negative term, eventually this T delta S term is going to get larger in magnitude as the temperature increases. Thus, that's going to overcome the exothermicity, the negative nature of the delta H term, and that's when delta G will change sign. So I just need to get that into words. Since the delta S term, delta S is negative, the T delta S term is negative. As temperature increases, at some point, the absolute value of the T delta S term will exceed the absolute value of the delta H term, and the sign of delta G will change. Lots and lots of different ways to say it. Lots of ways to earn those points. Theoretically, the best yields of ammonia should be achieved at low temperatures and high pressures. Explain. So, which one do you want to do first? I'll do it the way they gave it to me. Low temperature. The reaction is exothermic. Therefore, removing heat, also known as cooling. Throw it in an ice bath. Drives the reaction forward, making more product. Which is our ammonia gas. You don't have to put that part, but I just want to remind you what was going on here. Okay, so the reaction's exothermic, so here's what you need to be thinking. A plus B yields C plus D plus heat. If I keep taking this heat out of here by cooling down the process, doing it at a low temperature, then the reaction keeps driving forward to keep trying to replace that heat. That's what equilibriums do. So conceptually, that's what's going on there. High pressure, That's about squishing molecules down to the least number of moles of gas. 4 moles of gas in equilibrium with 2 moles of gas in this reaction. Therefore, an increase in pressure forms the product better. Favors, let's say favors the product side of the reaction, producing more ammonia gas. And there you have it. That's it. That's all of the AP essays I have on Thermo in my personal library. Again, God love you if you stayed to the bitter end. I hope you didn't. I hope you use these videos in a way that benefits you most, and I hope you have a fabulous rest of your day. Thanks so much.